Isabelle Braems describes her attempt to use artificial intelligence and machine learning to reveal the structure of molecules. Knowing what the component atoms are of a molecule, can she get their structure?
So my talk here is about structure search. So we're interested in structure because we know that atomic structure, the scaffold at the atomic scale, defines macrophysical and chemical properties. So it's very useful to be able to know the structure of the material in order to identify it, for instance, or to predict it, or things like this. Problem is we don't have rules to do that if we don't have access to the material directly. We don't have guides to be able to guess the structure of material only based on the chemical formula. Same for molecules. So for very long it was even considered like a scandal that it was not possible to do things like this. But suddenly we realized that AI tools could help. Why they differ from classical tools that we can see in other stuff. And talks is mostly about the fact that usually the mainstream part of AI for material science is property prediction. So you're looking for the best superconductor, you're looking for the best reactive molecule for an application or something like this. So you're not really looking for the structure as long as you get the property. So that's like a second order result. So looking for the structure was something like a niche till now, because it's much harder. And why that? Because you have to be able to represent the structure inside the computer, do your work of analyzing, and reverse all this to go back to the structure. They're actually a very nice way to understand the importance of this is to see that AI for molecular generation is much more developed and much earlier than what happened to crystals, mostly because it's much easier to get interesting representation of molecules on computer than with crystals. So there are many ways of representing it, for example, using strings. So that's only for molecules, and using some other stuff like graphs. Molecular graphs are very famous. And there are plenty of other ways, like image, like 3D voxels and things like this. All of them have their advantages and disadvantages, and because of that, they impose the structure of the neural network you're going to use. So that's the first stuff, that the data representation will impose that. And the second point is, because of that, you will have to know that if you want to stick to classical discriminative data, AI, all you can do is classify data. Means all you can do is saying that this structure is either with this property or this property, like the same way you say a picture is a cat or a dog, but you cannot say more about the structure than this. So you can't use classical tools. You have to turn to, if you're sure that the structure is not in your database, so for example, complicated structure, exotic new structure, which is my field of research, discovering new structure. So you have to turn to generative AI. So there are 4 ways to do that, and there are specific generative modeling, which are very famous for other fields, like image, which are generative adversarial network, GAN, we say, variational autoencoders, diffusion model, which is very famous for daily and things like this, and GPT for language processing. So transformers, more generally. And all these methods can be applied in the molecular and or the crystal field to generate crystals or molecules. The difference I make on this is because the representation is different, mostly saying that for molecules you can define them as strings, which you cannot do for crystals. For molecules you can use all the transformers strategy, which is a very booming approach these days. I'm talking about last year, maybe 2 years ago or this year, which is developing GPT for molecules, like MolGPT and plenty of other stuff. So because you can encode molecules like strings, and you can decode them as strings, then you can have access to at least a large part of information about the molecule structure using exactly the same kind of tools like classical GPT that you use for discussing, chatting, which are based on attention mechanism and some other mechanisms that we could discuss in another situation. Probably all I'm saying now is going to be outdated in 1 year, and I'm giving a talk on teaching classes on this, and I have to update this every 6 months because it's changing all the time. So for example, you can find very nice papers like 2020 saying that definitely molecular graph is a way of representing molecules because it's the best way, blah, 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 blah. And definitely strings are going to disappear. And the paper as a review is very good, but the review is from 2019 or 20. And since then, they've been developing GPT. And GPT is based on strings, so strings is back as the best description. And because string cannot be done for crystals, crystals are a little bit behind. Well, from a time point of view, they're going to catch up. And there's a lot of, but there are still a lot of criteria to define. One of the very important criteria that transformers do, and not other structures, is that you're quite close to be completely sure that the structure you're going to create is valid. Doesn't mean it's true, but it's valid. Means it's chemically valid, it makes sense. The rings are closed, the nature of the bonding would make sense, and so on. The same way ChatGPT is not saying the truth, but is developing a consistent language. So there's a context, and it's consistent within this context. So same for molecules, it's consistent with a chemical context. So that's very interesting because not only you can inverse a structure coding, but you can ensure that even if you generate new samples, that's the idea of generatives, creating new samples, some of them would make sense, or even most of them. There are some ways where you can create a lot of interesting structures, but they don't make sense. So you still have a lot of filtering after that to do. So all these criteria are developing that very interesting field to do right now. There's another part in artificial intelligence which is global optimization, and which is still my favorite because when you compare both of them till now, and probably that won't be true in 1 or 2 years, but till now, they're still competing. I like it more because it's more like answering the real question without adding a lot of infrastructures to solve it. That means it's a self-learning technique, you don't need a database. All the techniques I've been talking about, they need learnings, they need big database, but when it comes to generative, they need very big database. MolGPT has 6 million parameters to fit. You can't do that on the small database like classical one. You need really, really large ones. Global optimization is saying like all the interesting structure I'm really looking at are the stable one, the metastable one, depending on the chemical way of building them and things like this, and no others. So it's like a minimization problem. You're just looking for the lowest energy structure, or the global minima or the local minima. So that's really a math problem, saying that I just have a surface that we call the potential energy landscape, and I'm looking for the minimum of them. I cannot do it exhaustively because that's exploding. It's combinatorial very soon, even for small molecules, when you want to functionalize them, they're exploding. Same for crystals. But you can have nice tools to explore it. And one of the very nice interests of that is when you explore to look for the stable, you gather the metastable at the same time. So you have all this information inside at once. So how does it work? There's plenty of very nice tools to do global optimization, but most of them are bio-inspired, like particle swarm optimization and genetic algorithm. The one I'm using most is genetic algorithms. There's plenty of software to do that. And what are they looking at is they are doing combinatorial, proposing structure, computing the energy, ranking them, and looking for the best one. It's called genetic algorithm because it's derived from the famous Darwin idea of the fittest survive best. So the idea is you explore the space of all structures by taking some of them randomly first, that's a population, and then you mix them, so you create new structures that don't have to have a chemical meaning, and locally you relax them to get the local minima, and then it's like a new generation of children, and you compute if these children fit better or not than the parents. And then you go on, and you can show, even if you cannot prove it, that you will converge to the minimum. So I do that on plenty of examples, mostly for eco-responsible materials. So it's like oxychalcogenides, oxides, sulfite, nitrite. I'm very happy to see that industry is starting to be interested in this. So I'm working with experimentalists from academics and even industry now. So that's kind of very interesting. So I'm doing this kind of prediction for material design, but that's the same tool to get for structure search in aerospace, astrochemistry and things like this. So they are still efficient. I like the idea, but they have plenty of drawbacks, like for example, they're not transferable. And so they can be heavy if you still go with DFT methods, but you can go to machine learning potentials. And so there's plenty of still benchmark to do on that, but that's plenty of nice ways. And I like to finish my speeches, like talks or lectures on this, by asking the audience a question. Is this like, when you know all these tools, do you believe that future is about more artificial intelligence or no more artificial intelligence? And usually everybody's telling me that listening to the talk, everything's going to more. It's not that obvious, because parallel to that, there are some other people which are mathematicians, which are saying if all this is actually just a constraint minimization problem. So if I can write it as a mathematical problem with constraints, which are geometrical constraints, chemical constraints, and solve it not analytically, that's programming, but not so far. This is much cheaper, less energy consuming, and you can have something that is easily transferable to plenty of systems. So there are some papers that are very niche about that, but that's a way of solving problems, for example, for nanotubes. And there's another nice paper in Nature where they show that you can look for optimality. The point about this paper is it's just a window toward the future, because to implement this, you need now quantum computing. So, but that's most of the idea linked together that gives direction of research. So I'm just finishing by saying that it's a very interesting field. It's been a niche for very long because we were mostly focusing about discriminative AI, so the structure was out of reach. Because of generative AI, we can go much, but global optimization was there for a very long time, and it did a great work, and I still believe it's doing. And generative modeling is just showing up and bringing a lot of new information, but there's still some tests, some calibration to do, and see what the future is going to be about. Thank you.